To give this talk today, so I'm going to talk about some recent sort of experimental schemes which we were started to develop to probe more the thermodynamic properties of two-dimensional materials, and in particular magic angle twisted bilayer graphene. And so basically, as Andre already took away, basically one of the sort of puzzling aspects of the phase transitions in twisted bilayer graphene were that we were observing through transport and STM predominantly, two type of different experimental observables. So first observable, of course, had to do with metallic behavior of itinerant electrons that can freely move throughout the entire device. Those were, of course, the metallic states, the superconducting states, and the topological states. And of course, we observed also over the years many different sort of topological states, like is seen here with the topological Chern insulators. And then, of course, the other sort of side of the story is that also in integer fillings, of course, there were a lot of localization effects. We observed correlated insulator states where the electrons really would localize on the lattice sites and form Mott-like insulators. And so to bring sort of those two type of effects into sort of a unified picture, we were trying to do some experiments which go a little bit beyond the typical transport measurements that we used to do, and to try to do some thermal measurements. And this is something which is sort of the motivation of the talk, but throughout the talk I'll show you some of the recent measurements on the Seebeck effect in magic angle twisted bilayer graphene. Then I'll show you some sort of ongoing development that we were conducting over the last 5 or 6 years, where we were actually trying to develop a new a measurement technique to actually extract the heat capacity of two-dimensional materials in general. I'll talk a little bit about why this is really complicated and sort of what type of advances we have achieved. And last but not least, I'll also show some recent applied sort of studies where we actually were using superconducting twisted bilayer graphene as an ultra-sensitive bolometer that can detect single photon quanta. Okay, so basically, starting with the Seebeck effect, so basically we were quite inspired by the recent experiments by the Yazdani group, for example, or by the group of Shahal-Ilani, which were able to do compressibility or tunneling measurements to deduce some thermodynamic quantities out of the phase transition of twisted bilayer graphene. And so I think one of the striking results that, for example, Shahal observed by measuring inverse compressibility was this really strong asymmetry in the signal when he was going across the phase transitions of 1, 2, and 3 electrons per Moiré unit cell. And this is something which you can see here really well, where really if you sort of start at a filling factor 1 here, if you go to the whole dope side, you get a very asymmetric signal versus if we go to the electron dope side. And of course, these measurements also were confirmed by measurements, for example, at Shubnikov-de-Haas oscillations, where we typically, across these phase transitions, we would see sort of on the electron side, we would always see strongly pronounced Shubnikov-de-Haas oscillations, but not on the whole dope side. And so before that, so basically with sort of Shahal's paper, the theory that has been developed was the Dirac revival picture, that every time when we start filling up the band until integer fillings, we fill up all the flavors that go along with it. So starting from 0, we fill up all the 4 flavors, spin and valley, and then when we go across these phase transitions, some of the valleys are basically emptied out, and only one of the flavors actually survives. Okay, so we now also were inspired by the experiments. So what we try to do is now to go and measure thermal electricity measurements. So how do we do it? So actually, thermal measurements are generally notoriously hard in two-dimensional materials. I'll talk about this in a second. But basically, what we try to do is we would try to come up with an experimental scheme that uses the following setup. So we are having 2 split gates on top of the twisted bilayer graphene. These 2 split gates we can use to locally modulate the carrier concentration of the Fermi energy in the 2 different regions of the device. We can put 2 electrodes along the direction of this split gate, and then we can also apply some heating pulse in terms of a laser light that locally heats the electronic temperature in the device. And basically, the schematic that you can see here is the following. So we have basically a PN junction, and we have a thermal gradient across it. And I'll justify a little bit more why really this type of experimental scheme works out here. Okay, so and basically what we see here is the following. So basically, first thing is, of course, we like to characterize our gate function with the two split gates by measuring sort of resistance as a function of the two different gates. And what we see here is basically this map. So again, this is Rxx as a function of left gate and right gate. And we see this really resistive regions at filling factor 1, 2, and 0, of course, and also depending on which gate we tune. So we see this characteristic checkerboard picture that arises. And again, all of these states that you can see here as lines, those are referred to these correlated insulator states that we also see in transport experiments, right? So here, filling factor 2 is the strongest insulator that we have here, which you can see here very clearly. So along this line, we also, of course, then would shine the laser light on our PN junction after calibrating everything in quite a detail, and we would try to basically follow the photovoltage signal that we observe in the system and try to sort of overlay it with the resulting resistance map that we have. And you can see the photovoltage signal here. And so basically what you immediately can see is that really along these sort of trajectories of the insulators that we can tune, we also see some sort of oscillating features in the photovoltage that oscillate along with it. And really, to understand the mechanism that we are actually measuring here, what came really handy is to zoom in on the charge neutrality point. Right, so the charge neutrality point, if we zoom in at this picture here, we observe this characteristic 6-fold pattern when we, again, look at the photovoltage as a function of the two gates, whereas the NP region here remained strikingly positive, the PN region remained negative, and then in the NN prime and N prime P, N and P prime P and P prime PP regions, we observe basically sign changes, which is something which is very indicative of a photothermoelectric effect, because from a photovoltaic and other effects, you would not expect this type of sign change in these sort of equal polarity regions. And so this is something which again was done by actually Pablo back in the 2011 at single layer graphene. So this is really well understood and is taken basically as a signature of the photothermoelectric effect. So basically the photo-induced laser beam, it really acts as a heater to the PN junction and it induces a temperature profile that drives the photoconductivity in the system. Okay, so basically what we can do with this measurement scheme now is we can simplify sort of our measurement a little bit. We can tune one of the gates to charge neutrality point, basically locking the Seebeck coefficient to 0, and we can basically take a full photovoltage trace as a function of filling factor, just tuning one of the sides of the PN junction. And this is what we're seeing here, and we see basically very many features. In particular, we see at charge neutrality point the well-expected feature where we see a sign reversal of the Seebeck coefficient when we go from hole to electron side. So on the hole side, the Seebeck coefficient is positive. When we go to the electron side, it becomes negative. And overall, it's symmetric between sort of the electron to hole transition. And this is something which we know really well in single layer graphene, for example. So this is data from the Philippine group for various works like a couple of years ago. And so basically, this is very well understood that at charge neutrality point, upon sign reversal, you get this basically S-type of shape, sign reversal, and symmetric behavior across the charge neutrality point. So however, we, in magic and graphene, we have, of course, many other gaps. As I showed before, for example, we have the filling factor 2 gap, which is the strongest gap here in the system. And you can see across these gaps here, for example, filling factor 1, filling factor 2, we observe a very different picture. We would expect, naively, a very similar behavior that you can see here. Also, we get an electron-hole transition, and we would expect a sign reversal and a symmetric behavior of the Seebeck effect. However, as you can see, what we see is a sign-preserving effect and also a strong asymmetry between the two different sides when we go across the transition. In principle, very similar to the inverse compressibility measurements that Shahal was doing in his devices. So we were trying to really understand this effect sort of in terms of first principles, right? So just to get an intuitive understanding how can we expect this behavior. So Andre helped us with theoretical calculations. And basically, the two parameters that can be very important to change the signal to what we observe is mass asymmetry and lifetime asymmetry between the electron and hole excitations. And so basically here you can see what happens if we introduce some mass asymmetry across a gap and look at the Seebeck effect measurements, Seebeck effect signal that we expect from here. So we get a strong asymmetry, but we never can suppress the whole contribution of this type of behavior. However, if we would able to suppress this type of contribution of the Seebeck here, we could basically get a signal like that. And this suppression, actually, we can engineer if we assume a very short lifetime, meaning that the lifetime of the particle is very small and they scatter a lot, right? And this type of lifetime asymmetry, very low lifetime of the Hall excitations would definitely reduce the Seebeck coefficient. And if it's strong enough, it would basically result in the sign-preserving measurement. Also, as you can see here from the simple model, when you assume mass and lifetime asymmetry, you can really introduce this type of shift and suppression of the whole signal. However, of course, this is just an intuitive picture, so we were also very inspired by the topological Hamiltonian model, which again was developed by Andre recently, where he already talked about it in the previous talk. So, but really coming to the main sort of essence of the predictions and sort of tying it to the observables that we have, is that on a consistent basis, if they calculate their spectra with respect to the different ground states that you can find in the filling factor 0, filling factor 1, filling factor 2 states, there is an inherent and really repeatable asymmetry in the electron hole excitations if you look at filling factor 1 and 2, and there's always a strong symmetry when you sort of look at charge neutrality point. And this is exactly in line with what you're observing, so charge neutrality point is very symmetric sort of mass symmetry between electron hole excitations, which is not present here at filling factor 1 or filling factor 2. So the mass asymmetry comes naturally out of this, but on top of that, and this is again, I think, very, very crucial that this calculations can provide, they can also provide a measure of the lifetime asymmetry, and this is sort of the smearing that you can see here, right? And so basically, as you can see in this filling factor 1 and filling factor 2 states, there is a strong smearing of the flat band region of the heavy mass regions, which really reduces the lifetime of these bands dramatically. However, on the electron side, you get basically really long-lived itinerant electrons. So those two findings together, they're really explaining our sort of observables well, and they're really the two main ingredients that we can propose here that we observe across the integer filling states is really mass and lifetime asymmetry of the excitations. Yep.
All these descriptions are in terms of one of your densities next to the junction. Can you just explain once more what's the role of the other side of the junction, which you're keeping now?
Right. Yeah, we're keeping it. So basically. So the other junction, again, we're keeping just a charge neutrality point, and basically the Seebeck coefficient of the charge neutrality point is just 0. So basically it's not, the idea is, and we recalibrate this, is that the other junction does not contribute to the photovoltage. It just, overall the average signal is 0. So basically, but in principle, this is just to take a really nice line trace here to demonstrate the behavior, but in principle, yeah, this is just an experimental calibration to extract this value, yeah. But of course, yeah, if we would keep this mu2 at a different value, things change, but I think we can also model this. So this is not like changing the modeling that we do. Okay, so this is one side of the story. So I think let me shift a little bit of gears, and I wanted to just give you a more technical, so maybe this is more only interesting for experimentalists, but just more technical sort of development that we have conducted over the last couple of years. Because in principle, we were happy to do the Seebeck effect measurements, but what we really would like to do, this is sort of our dream experiment, would to measure the heat capacity of these two-dimensional materials, because this gives us direct information about the Hamiltonian, it gives us direct information about the free energy of the system, And for all of sort of the phase transitions that we observe here, this would be really the key experiments that we would like to do as the experiments that people are doing in three-dimensional crystals, right? This is one of the first experiments that everybody does, studying an interacting system is measuring heat capacity. And there are simple ways to measure the heat capacity in three-dimensional crystals. In two-dimensional crystals, heat capacity is really, really hard, right? And the reasons it's really hard is for the following. So basically, let me just explain to you the basic principle to measure heat capacity in a three-dimensional material, right? So you basically take a three-dimensional material, you try to thermally isolate it. So actually in school, if you take a heat capacity measurement of water, you usually would fill in the water into some styrofoam, to a very isolated material, and then you would try to heat the water up with time-dependent behavior. Right, so basically the idea is that we have the crystal, we have heat capacity of the material, we have a very weak link that isolates it thermally from the environment, and we would conduct thermal relaxation polarimetry, meaning that we would apply heating pulse to the material, we would record the temperature of the material, and then we would also look at the thermal relaxation time of the material, which basically by this formula would give us the internal heat capacity of the material. Right, so this all works really well for three-dimensional materials. For nanoscale materials, it becomes really hard because you have to isolate the material dramatically. Your material might have extremely low heat capacity, which is much lower than the surrounding environment, much lower than the silicon oxide chip on which the device sits. So things become really hard. And on top of that, we don't have typically good thermometers to study sort of to measure these properties, because thermometers have a much higher thermal mass than actually the material itself. So basically the challenge here is really that thermometry is a challenge, and the other challenge is that thermal relaxation times in 2D materials, because they're strongly coupled to the environment, is usually ultra low, and the thermal relaxation time of graphene is, for example, usually in the orders of picoseconds. So in order to sort of copy this sort of thermal relaxation polarimetry scheme for two-dimensional materials, we would either need to isolate the system. So first of all, we would need to have a good thermometer, and second of all, we would either need to isolate the system dramatically, which is really hard, or we would have to perform the measurements on a picosecond timescale. Okay, so basically, in a nutshell, what we decided to do is decided to build a setup which basically uses optical heating, because optics can be ultra fast. Optics we know we can control in a picosecond timescale, and to also use a Johnson-Noise thermometer to read out the electronic temperature of the device. So basically, the way this works is that we inject a heating pulse, which is a laser pulse, onto our material. We use this Johnson-Noise thermometry heating scheme, which a lot of groups actually also in this room are using right now, in order to measure the electronic temperature of the device. And we can therefore really record on a temporal scale the electronic temperature of graphene as it changes. And so here is basically a scanning graph of our typical device, where we can scan the laser beam around, record the electronic temperature at the same time, and you can see, so really the signal comes directly from the graphene device. So without going too much into detail, this is basically an experimental scheme which on the Johnson-Noise thermometry, which has been developed by Casey Fong, and also Philip Kim was working on this quite a lot in the last couple of years. This type of basically heterodyne measurement scheme uses the Johnson-Nyquist theorem, which basically states that the power that is emitted by a graphene device, which is basically a black body radiation, is proportional to electronic temperature TE. And basically, if we record this emitted power with this, again, elaborated heterodyne measurement scheme, we can basically use this power as a calibration for our thermometry. And basically, long story short, if we integrate long enough, of course, this is a very sort of slow measurement scheme, we can get an electronic temperature readout of around 1 millikelvin. Okay, so using this thermometer, we can do already two things. We can use sort of the bolometric response in order to derive the thermal conductivity in the device. So this is typical calorimetric measurements of single layer graphene. So basically, we record the electronic temperature as a function of the laser power that we are absorbing in the graphene device. We get this typical nonlinear behavior that is typical for graphene because it cannot absorb too many photons. So it's an inherent nonlinearity, but in the low sort of excitation regime, we can basically use the bolometric effect to extract a thermal conductivity, which is again just absorbed power divided by the raised electronic temperature. And this electronic thermal conductivity, of course, we can then also study as a function of temperature, for example, to try to deduce the mechanism that is governing it, where we typically find this type of behavior that you can see here, where really at high temperatures we get a power law behavior of the thermal conductivity, and at low temperatures it basically saturates, and at lowest temperatures it becomes almost linear. And so the way we understand this type of behavior is that we have some sort of Wiedemann-Franz law, electronic diffusion into leads. At low temperatures and at high temperatures, thermal conductivity is governed by this power law, which is basically due to electron-phonon interaction. Okay, so this is the thermometry scheme. The other thing which we were able to do is to hook up like a time-dependent laser pulse. So this is basically, we used a delay line to heat up to separate two laser pulses with a time difference between them, and we were able to modulate the time difference between the laser pulses. So what this allowed us to do is to use the thermal, this nonlinearity that I showed you before, in order to also work out the relaxation time of the graphene device. So you can see here, so we observe, we've measured the Johnson-West power as a function of delay time. We observe these dips in the signal, which are giving us direct information of the thermal relaxation time, which is consistent with sort of other type of measurements that people done on the system, is in the orders of picoseconds and tenths of picoseconds, depending on the temperature you like. Okay, so long story short, we were able to combine, of course, these two measurements. So now we have our thermal conductivity, now we have our thermal relaxation time, and now we can basically combine these measurements in order to get an idea whether this works for our heat capacity measurements. Basically, the ballpark is already there, but we had actually, in order to not overheat the system, we had actually to change our experimental scheme slightly, where instead of these pulse probe experiments, we actually developed a photon mixing scheme, where we would basically mix two lasers together to create a continuous wave heating pattern, which basically you can think of it as two laser pulses, but now very short, sitting next to each other. And with this scheme, we were really able to push down also the noise level of the system that we were sort of observing. And here is basically just the results. So basically, this is heat capacity measurements of single-layer graphene close to charge neutrality point as a function of temperature. So we were able to really, below 100 Kelvin, we were really able to fit our data really nicely with some sort of simple predictions of the heat capacity of graphene. So below 100 Kelvin, we can measure the electronic heat capacity of graphene. We can also measure, of course, the heat capacity of graphene as a function of carrier concentration, which really follows the similar trend, however, with large error bars. And I think just the take-home message here is that really with this setup, we were able to measure the heat capacity on a sort of a picosecond time scale. So this measurement scheme applies to all 2D materials, which would have otherwise a thermal relaxation time, which would prohibit any type of measurements like that. So I have to say, so this is a work in development. So we're, you know, and of course, the dream would be to apply it to twisted bilayer graphene or to any other of the interesting two-dimensional materials that people are studying right now. One challenge is, of course, we still need to reduce the error bars a lot in the system. The other challenge is, of course, we were able to do it in an optical cryostat in 10 Kelvin. So this has to move in a dill fridge in order to really approach the temperatures that we are needing in these type of systems. Okay, so a couple of minutes left, right? So, okay, so just two more things that I wanted to talk about. So one thing is single photon detectors. Again, it's very technical. So basically, single photon detectors are detectors of single photons that a lot of quantum optics people use sort of in their labs. So I think in any quantum optics experiment lab, you will find a bunch of single photon detectors that people are using for photon counting and photon statistics, entanglement measurements, and so on. And basically, one of the leading technologies for these type of materials, detectors, is basically superconducting nanowires. Okay, so basically the idea is if you have a superconducting nanowire, you can make it really narrow and really thin in order to reduce the heat capacity in this material. And if you then absorb light quanta in one of those arms of this superconducting device, you can sort of heat it up above the superconducting transition and induce a photovoltaic pulse. Okay, so this is the basic principle, and of course, the lower heat capacity, the smaller nanostructure you can make out of these materials, the better. Okay, so basically an inherent limitation for this technology is that usually you use sputtered bulk superconductors which don't have such a low heat capacity. Okay, here is a chart basically of novel superconductors, so two-dimensional materials usually are much thinner than traditional superconductors. They usually have a much lower carrier concentration and therefore a much lower heat capacity than traditional superconductors. Actually, this carrier concentration can be orders and orders, 6 orders of magnitude lower than in traditional superconductors. So what we were trying to do here is we were trying to use one of those graphene superconductors in order to make ultra-sensitive single photon detectors. And I have to mention that this sort of idea and this work was, of course, also originated from a collaboration with Casey Fong, who basically made in the last couple of years sort of a number of demonstrations of single photon devices. So okay, so this is our experiment. So again, we use basically a similar device that I've showed you before in a similar setup. We shine laser light on it, and we measure transport behavior, right? So this is an IV characteristic of such a superconducting device. So we see that it really has this superconducting state in the IV characteristic, and we see that if we tune the bias close to a transition, we even have a hysteresis loop here. Okay, so we can use this type of hysteresis loop here by using a voltage bias electrothermal feedback loop, where we can basically bypass the current if the device switches, and we can basically record single clicks if we basically shine laser light on it. So here's basically a measurement trace that we can take with such a device. Right, where we basically recording clicks across the device as a function of bias voltage when we tune the bias voltage closer and closer to the superconducting transition. And so you can see we have really perfectly quantized events that we can record, which become much more dense until they saturate when we tune the bias close to the transition. We can then do statistical analysis on these clicks, so we can bin them up. We can also look at the Poissonian distribution of these clicks, which both of them basically are able for us to tell that it's really short noise event, those are random events that happen. And of course, the other thing that we want to do with such a device is to look at the count rate as a function of absorbed photon number. And the count rate that we find is linear with absorbed photon number and not squared or not to the third. So this also allows us to deduce the information that it's consistent with single photon events. Okay, so last slide, just to say something that we are personally also working hard on and really excited about. So we were also very inspired by the recent QTM developments by Shahal Ilani's group, and we are really diverting a big effort right now in this direction. We already have a working QTM in the room temperature domain, so we have already really nice tunneling spectra that we can take with our room temperature QTM, and we also have a low temperature QTM, which we're testing out right now. So with this, I think, thanks a lot for your attention, and happy to answer any questions.
Questions?
So Dimitri, on one of your slides on the bolometers, you said that there was the prospect of extending the spectral range by using these superconductors. Can you comment which figures of merit are important there? You talked about carrier density being lower, enhancing sensitivity, but what comes into what spectral range you can use?
So this is about the heat capacity, or?
No, this was the bolometry, the single photon bolometry.
This one, right? Right, so basically, okay. So to take it away, so what we are really interested in is long wavelength detection. So basically, these detectors work usually in the near R, so at 1550 telecom range. This is actually good because all the quantum optics people use this range, so it's like very convenient. But this technology is already pretty mature, and there are companies who sell this equipment, right? So we don't have hopes to improve this type of thing. What these materials fail, however, is at long wavelengths like terahertz, and you probably cannot detect single photons beyond 8 micron wavelengths.
So what determines that?
The heat capacity determines this, right? So because this material, we all do nanofab, right? So we know what the challenge is. This material is usually 10 nanometers thick. So if you spot a superconductor above 5 nanometers, that's only when it becomes superconducting, right? So 5 nanometers is thin, but compared to twisted bilayer graphene, it's 10 times thicker, right? And then the other thing is the number of electrons that you need to excite to overcome the superconducting state. And if you look at sort of typical materials like aluminum, niobium, and so on, they have a huge carrier concentration, right? They have like, per sheet, they have 10 to the 17 electrons, right? So if you reduce it, you use twisted bilayer graphene, it already has 6 orders of magnitude lower carrier concentration. So if so we calculated, we had a theory sort of paper on this. We calculated that really, if you use magic and graphene, you should be able to detect single terahertz photons. So this is something which we're doing now. This is actually the real selling point of this development, I would say.
So your GBAC measurement onto this twisted layer, what is the temperature increase with the laser power?
Right. Yeah, so basically, this is something which we calibrate quite accurately, so this is an extra slide. Right, so this is also on the side of the paper, right? So basically, we try to stay very low, right? Because in principle, for laser, you can heat the system by hundreds of Kelvin if you want. And with these pulse lasers, you can go up to 1,000 Kelvin. So here it was important to really reduce the power with which we measure to sort of below 1 Kelvin excitations. Mm-hmm. So we did some heat capacity estimations. What is the laser power with which we stay below that? And so here is basically, again, this is the Seebeck measurement, so the photovoltage is a function of PL. So we're really trying to stay at the few microwatts. Uh-huh. And also what we checked is that we checked by changing the laser power for the different curves, we checked that the curves don't change, right? That we would, if we would heat them very much up, we would be able to tell that, right? They would start looking at like high temperature measurements. Right?
So the temperatures are lower than that any gap opens up in the part. Right. But then I got a little bit confused. How do I get this both kind of carrier contributions and then?
Right. Oh, okay. So the other thing is I wanna say so, right? So basically, what is really important here, right? Right. So what's really important for, maybe this is maybe the right slide, right? So this sign conserving behavior. It's not like generic. It depends on the parameters that you use, right? And it's really reliant on a finite temperature approximation, right? Mm-hmm. So if we would go to 0 temperature, we would have then we would not see this, right? We would see again this sort of a negative Seebeck coefficient. We would need to sit at finite temperatures in order to populate both bands, right? So the KBT has to be in the kind of in the order of the band gap or of the mm-hmm. energy gap that we have, right? Okay. And so we actually did also temperature dependent measurements. So we also took the measurements at like around 30 or 50 Kelvin, way above. And this is where we also see sort of the population or the population of the entire band and also higher order bands. Where, for example, this positive behavior here, this is exactly coming from this overpopulation of the two bands.
Okay, great, thanks.
I have a maybe follow-up naive question about the Seebeck effect. What part of the results that you see are not explained by something like the revival model? Because even there you would expect that as you do this revival, you keep populating the same sign of electrons.
Right, okay, so all right, the first order thing that is different is that, in principle, the revival model does not even account for gaps, right?
Yeah, but a simple expansion can account for gaps, but still it looks very similar to the.
No, so I think this is also a question to Andre then, right? But I think as far as I understand, the heavy fermion model explains also the Dirac revival. They're kind of consistent with one another. I think the advantage of the heavy fermion model is it gives now microscopic and real spectra with which to think. But I think our data and Shahal's data are consistent. They're looking at the same finding. It's just the theoretical explanation, but maybe, yeah.
You would get positive and negative. You can't. I mean, we can talk about it afterwards, but you wouldn't get, you would get a positive peak for holes and a negative one for. Oh, thank you. All right. You've got an insulator, you've got a gap. You would get positive and negative peaks for holes and electrons. So it's, there's no way to get negative for both electrons and holes around integer filling without assuming some lifetime asymmetry. Or at least, if there is a way, then, we want, a challenge to explain it. We don't see a way.
Maybe after this question, we can open it up in a few minutes also to questions for both of the speakers from this morning.
Just testing this heavy fermion description, I mean, do you have an estimate of the Kondo temperature from the experiment? And
Oh, no, we cannot do that.
I was just curious if you could try to get some sort of T over TK scaling in the Seebeck if you're well below the Kondo temperature in the heavy fermion liquid regime, which
No, I don't
you
think,
see in Kondo,
I mean,
Kondo
I
physics.
think, no, I think that we cannot extract that, right? I mean, what we can extract is an ordering temperature, right? This is when the insulators appear. This is also when this asymmetry appears in the measurements, right? This is sort of the ordering temperature, which we know is, in the best case, it's like 15 Kelvin or something like that, right? And above that, also, right, I mean, the Pomeranchuk effect, which Andrea showed, above that, things become different, right? But the Kondo temperature, no. I mean, we discussed this a lot, how to actually probe it. I think in STM, maybe there are some signatures, but not from this, right?
That's really a question for Rocco.
Interesting, thanks.
Any questions for either speaker? Oh, is there one? Yeah, sure.
The point is that the problem is that you reach these symmetry broken phases before you can reach the Kondo temperature. And in fact, all the calculations that were shown here, they are already in the symmetry broken phase. So if we suppress the symmetry broken phase, then you would be able to see this Kondo temperature. But the problem is that you reach at these temperatures already, the symmetry broken phase, and you cannot reach the Kondo temperature. That's at integer fillings. Yeah.
Maybe I'll have a question for Andre, but so in this heavy fermion description, it's very lattice-based, and it's a lot of that is coming from inspired, as you said, by some experiments with entropy and local moments and so on. But the same exact experimental signatures are seen without any lattice in all of the crystalline graphene. So what's the current thinking on that? Ongoing. Okay.
I know your experiments, and they're. But then
you published something already, or
On archive. Yeah.
On archive.
Some weeks ago, yeah.
But then so Tim Welling has this description, as you know, because we've been corresponding.
Yeah, but so what's? It's not like I understand anything. So
Tim Welling
sort of
has
what's
this
the
description where he actually tries to linearize the bands, below, without a Moiré, right, to obtain a Fourier description. So that might be one way of doing it. I'm very confused by your, obviously thought expiring.
Okay, I'll have a look. So yeah, I heard something.
Confusing.
But
Yeah.
Right.
Other questions? We have a few minutes.
So if the heavy fermion picture is a way to get the EM model, and that's one of the things that you carefully show, do we need to work with heavy fermion picture? Can we just work with BM model?
Right. So I think,
Like, what do we gain that's new?
I mean, okay. So this is.
So there must be something that you gain by doing this hard work. So I want to know what that is.
No, I got a question. It's a question to Andre, but I think in my understanding, the lifetime broadening, that's something, the lifetime, that's something which you get here very easily, right? Which you don't maybe necessarily get otherwise. And again, in our sort of really to sort of match our findings, right? We really need this lifetime asymmetry. It's more important than the mass asymmetry. So I mean, this is sort of piece right here.
So here's what you don't get if you just work with with a BM model. So there's a paper that does Monte Carlo, quantum Monte Carlo at half filling, which is the only place where they can do it because they don't have the sign problem, by Eritzberg. There's a bunch of co-authors, and they do find the Hubbard bands. Now, if you work with the BM model in the k-space formalism, you're never going to get the Hubbard bands. So you need DMFT and in the heavy fermion description, they're clearly there. Now, there's another question, which I don't know if Oscar is going to touch on it, but the question whether the Hubbard U is as large as the one that's derived. If it's not, then we've got another issue we don't understand. But Eritzberg's paper clearly shows that you get Hubbard bands. Those ones you wouldn't get them from the BM model plus in momentum space.
What's the interaction?
Same interaction. They're using BM plus Hubbard plus Coulomb, but they're doing quantum Monte Carlo, so it's an exact method. So they do see Hubbard bands there, which you wouldn't get, which you get for free, or not for free, but they're obvious in a heavy fermion description, but not in a BM Coulomb in momentum space.
Yeah, this is a question for Dima. So one way to check this model is to do the same experiment at very low temperature. And maybe you said that.
Yeah.
So then you should see again the positive and negative.
Yes, exactly. So this is, again, this is type of the heat capacity measurement. So we need to transfer the setup into a dough fridge. Right now our base temperature is 5 Kelvin, but we would like to go below that. And actually, the single photon detector is already done in the dough fridge. We don't have a focused light, but we have. But now we're working on introducing sort of scanning. So, but this is in progress. But no, I cannot say anything right now, right? Yeah.
Just a comment for you. There's been some measurements from Klaus Eslin's group of the specific heat from gate-defined Josephson junction measurements. We're measuring on twisted bilayer graphene is used as the superconducting gates and the insulating barrier. Right. It'd be interesting to compare.
Okay.
Yeah.
Right. Okay. Yeah. What did we get from Josephson junction heat capacity?
Yeah. The whole thing is TVG. It's like
One more question over here.
All right. Okay.
I can show you the other.
Right. We'll sort of go back to Andre, but you're welcome to answer it as well. The title of Andre's talk was Pairing Symmetry of TBLGs. What is the pairing symmetry?
Where is the pairing symmetry?
What is the pairing, not where?
What is the pairing symmetry? P plus IP, and it's a 2D representation.
So did you say that, or did they miss it?
There was, I had to give, there's 4 anomalous whole talks. I had to give, I had to give my fractional journalist little talk too. So there were two
all right,
slides.
okay.
I mean, that's you get a fast talk if there's a time asymmetry in the invitation. Sorry, it's a gapless superconductor. Gapless superconductor, gapless triplet. But as you know very well, those are those predictions. I'm not going to stick my hand out. Nobody's going to stick their. Well, they're like one millielectron volt. It's very small. There's a lot.
That's exactly where we keep
Okay, as far as I know, KITP rules allow us to go to coffee slightly early, and we should probably do that. So let's do that. Thanks.